Yeah, here you go. Yeah. Great, yeah. So we are pleased to have our last talk for this section. We have from Dr. Rathod. Yeah, actually, I'm sorry if I cannot pronounce your first name. Hopefully, if and it's joined with work with Tomade, right? Okay, please go ahead. Right.
Okay. Thank you. Hello, everyone. My name is Abhishek. I'm a postdoc at Ben Gurion University, and I'm really excited to present this talk at this workshop. Today, I'll be talking about cup product persistence and its effective computation. The talk is based on joint work with Tamal Dev when I was a postdoc in his group. Let me begin the talk by recalling how the cohomology ring is finer invariant compared to homology groups. So the most elementary example that comes to mind is when you compare a torus with the space that is formed by taking the wedge of a two-sphere with two one-spheres. So it is easy to check that they have isomorphic homology groups, but their cohomology rings are different. So this naturally motivates the question as to how you can use the cohomology ring structure to define and compute finer invariants in the setting of persistence. So that's the topic of today. So here's a list of prior work. This list is not exhaustive. Of these prior works, the most relevant to our work are the first two references. So that's because we design fast algorithms for computing invariants that are defined in these papers. And of these prior works, the most relevant the papers that are most close in spirit to our work are the first and third papers, because the focus is on algorithms and computation, just like our work. And now I'll give a quick summary of the contributions of this work. So there are three main contributions. So we devised the first algorithm for explicitly computing the so-called persistent cup modules, which were introduced by Contisetto et al. The algorithm runs in ODn raised to 4 time, where D is the dimension of the filtered complex and N is the size of the complex. And there is another variant that was defined by Contisetto et al. Called the persistent cup length. And they observed that this the persistent cup length can be read off from the barcode of the persistent cup modules. So our first algorithm also translates to an ODn raised to 4 algorithm for the persistent cup length. Now, this is in contrast to the ON raised to D plus 2 time algorithm that Contisetto et al. Provided. So our algorithm is already fast compared to the algorithm for D greater than or equal to 3. And apart from these two invariants, the third invariant that we'll be talking about today is an invariant that we define in this book, and that's the partition module of the cup product. And so we define this invariant, we show how to compute it, and we prove that it's stable. And computing each of these partition modules takes O(n) raised to 4 time, and there are at most sub-exponential number of them. So if your D, that is the dimension of the complex, if that's all, which is the typical case for TDA applications, then computing this entire invariant is not that expensive. So what we'll be looking at in this talk will be the definition of these three invariants and some examples which tell you which invariants are stronger compared to the other invariant. And also we'll be looking at the algorithm for computing the persistent cup modules. So before I go to those details, let me quickly recall some preliminaries. So as everyone knows, what the cup product is, but I just want to give like a brief introduction so that I can make some definitions. So we'll be working with graded co-chain complexes and graded cohomology vector spaces. These are obtained by taking direct sums of the p-degree counterparts. We denote them here by C star k and H star k. Now, if you're given a complex k, then and two co-cycles, a p co-cycle xi and a q co-cycle zeta, then we want to see how to define the cup product of these two cocycles. So suppose that you're given an ordering on the vertices of the complex, and say you have a simplex sigma, which is a p plus q dimensional simplex, and the vertices are written in order from v0 to p plus q. Then the cup product of these two cocycles is given by the first cocycle xi evaluated on the span, on the simplex span by the first p plus 1 vertices multiplied by the second cocycle zeta evaluated on the simplex that is spanned by the last q plus 1 vertices. So this gives us a map from C star k, product C star k to C star k. And using the universal property of the tensor product and the Leibniz rule, we also obtain linear maps from the tensor product of C star k, tensored with C star k to C star k, and the tensor product of H star k with itself to H star k. Note that we denote all these maps using the symbols cup. Let me now also briefly recall some preliminaries of persistent cohomology. I assume everyone here is familiar. So I just want to say that for the purpose of this talk, the poset that we'll be considering will be the poset defined on indices 0 to n. In the paper, we use posets which are like integers or reals. But I just wanted to keep the notation simple. So here we just consider this poset. So the setting is that you are given a d-dimensional complex K of size n, and you have a filtration as shown here. Then applying appropriate functors, we obtain two persistence modules. The first persistence module is basically C star K bullet, which is where the objects are cochain complexes and the internal structure maps are cochain maps. And the second persistence module is denoted by H star K bullet, where the objects are cohomology vector spaces and the internal structure maps are linear maps. Now that we have the setting, let me also recall the notion of image persistence, and so that we can use this notion to define so-called persistent cup modules. So say that you have a persistent module of chain complexes C bullet shown on the left, and another persistent module of chain complex D bullet shown on the right. Then say that we suppose that we have a morphism G bullet from between these two chain complexes, cochain complexes, persistent module of cochain complexes. Then if you apply the cohomology functor H star, you get another morphism H star G bullet. And when we talk about image persistence, the persistence module of interest is basically the image of this morphism. So now if you consider the morphism given by the cup product from C star K bullet tensor C star K bullet to C star K bullet, and we call this map the cup map. And if you take this cup bullet to be G bullet in this previous definition, then the persistence module or the image persistence module thus obtained is called the persistence cup module. And likewise, if you take the image persistence of the k-fold tensor product of C star K bullet to C star K bullet, then the persistence module thus obtained is the so-called persistent K cup modules. Now, these notions were introduced by Contessa et al., but their definitions are somewhat different. So we believe that putting them in the setting of image persistence simplifies the definition and also leads to a simple and efficient algorithm for computing them. So before we get to the algorithm, we want to look at what are the properties of these modules, like what are the structure maps, what are the birth and death indices. So we prove these elementary properties. So the structure maps of these persistent cup modules are essentially the restrictions of the structure maps of ordinary persistent cohomology module to the image of the cup map, cup bullet that was defined in the previous slide. And the birth indices of this persistent cup modules are the subset of the birth indices of the ordinary persistent cohomology modules, whereas the death indices of this persistent cup module are the subset of the death indices of the ordinary persistent cohomology modules. And the question is how many intervals in the barcode of the cup module can be born and die at some index. So it turns out that many can be born at a birth index, but if D is a death index of a persistent cup of the ordinary persistent cohomology module, then it can be the death index of at most 1 bar in the persistent cup module. So this is something that is also eventually used in the algorithm. Now I want to define the next invariant, which is the persistent cup length. This is also introduced by Contessa et al. First, I will start with the definition of a cup length of a ring. This has nothing to do with persistence. It can be defined for any ring. So the cup length of a ring is defined as the maximum number of multiplicants that together give a non-zero product in the ring. And now let int star denote the set of all closed intervals of the reals. Then for an R-index filtration of simplicial complexes, the persistent cup length function as defined by Contessa et al. Is the function that assigns to every interval AB the cup length of the image of the ring homomorphism H star KV to H star KA. So that's the second invariant that we compute in this paper. And then there's another invariant that we introduce, and it's the partition modules. So before I define what this partition invariant is, let me recall what integer partitions are. So a multiset lambda q from S1 to SL is a partition of the integer q of size L if the sum of S1 to SL is equal to q. Now we can define the partition invariants. So we can define a partition invariant lambda q for every partition lambda q of every integer q. And we denote this module by W lambda q bullet. And so what are the vector spaces and what are the structure maps for this module? So the ith index vector space for this module is given by the span of L-fold products of cohomology classes alpha 1 to alpha L, where alpha 1 is of degree S1, alpha 2 is of degree S2, alpha L is of degree SL, and so on. And the structure, the ith index structure map for this module is given by the restriction of the ith index structure map of the ordinary qt degree persistent cohomology group to the ith index vector space of this partition module. So it's easy to check that this module is actually a submodule also of the persistent L cup module. So now that we have defined a partition invariant for every partition of every integer, the question is how many of them are there. So say you have a filtration of a d-dimensional complex. So how many partition invariants do you have? So it turns out that this number is actually quite small for small dimensional complexes. Small dimensional complexes constitute the typical use case scenario for TDA applications. And as you can see, when this dimension is small, you don't have many invariants, but this still gives something that's stronger than what has been seen so far. So we also show that this invariant is stable for RIPs and check filtrations of finite point sets. Now that we have defined what this invariant is, we want to see how strong it is. So if you are given to simplicial filtrations that have distinct cup modules, then their partition modules are also distinct. So this tells us that the partition invariant is at least as strong as the cup module invariant. But the question is it stronger? So here's an example which tells you it's stronger. So take a complex K, which is given by the product of S3 and S1, wedge S2 and wedge S2. And a second complex is given by S2 product S2, wedge S1, wedge S3. And if you take the natural cellular filtrations on these complexes, then these are isomorphic persistence modules, isomorphic persistent cup modules, but they have different partition modules for the partitions 1, 3, and 2, 2 of the integer 4. So now we know that partition invariant is stronger. So now this begs the question, well, can you define even stronger invariants? So that seems to be the case. So for instance, if you take a 3 torus as a complex K and if your complex L is defined by RP2, wedge RP2, wedge RP3, and if you consider the natural filtration, cellular filtrations on these two complexes, then they have isomorphic persistence modules, isomorphic persistent cup modules, and also isomorphic persistent, also isomorphic partition modules. But if you just look at the complexes K and L, they have non-isomorphic cohomology rings. So surely we can define something that's even stronger. But in our opinion, defining even stronger invariants may not necessarily help, because at some point the cost of computing them would become prohibitively expensive. So with partition modules, we have the balance where the invariant is strong enough, but the cost remains low. Now, before I get to the algorithm, let me introduce some non-standard notation that we use in the algorithm. So, if you look at the barcode of the ordinary persistent cohomology module, a closed open interval j plus 1, I plus 1 is written as an open closed interval ji. And so basically there's a shift of index 1, and open becomes closed and closed becomes open. And we write the intervals j plus 1 infinity of the ordinary persistent, of the barcode of the ordinary persistent cohomology as jn. So again, j plus 1 becomes j, and infinity becomes n, and closed becomes open, and open becomes closed. In contrast to the usual practice, we define the left endpoint, which for these intervals is I or n, as the birth index, and the right endpoint, which is I or n, for these intervals as the birth index, and the left endpoint as the death index, because we go in the reverse filtration order. With this notation defined, I am now in a position to give a high-level description of computing these modules. So let V bullet be the persistent cup module for filtration K bullet, and this is the quantity that we are interested in. The barcode of this module is the quantity that we want to compute. Let's see how to do that. So you have to begin with first you have to compute the barcode of ordinary persistent cohomology, and let's denote this by BK bullet, and the intervals are given by BIDI. And now let omega be a persistent cohomology basis for ordinary persistent cohomology. So we will be using these representatives for computation. So what we essentially do is that we keep track of birth and death of co-cycle classes for the index K vector space in the persistent cup module. So observe that we go from n to 1. So you have a for loop that goes from n to 1, and that means that we are processing the simplices in the reverse filtration order. So what do we do in this for loop? So we maintain two matrices. So we maintain a matrix H, which basically maintains all the core cycles of ordinary persistence which are alive. But what I mean by alive is that for this index K in the for loop, this K is between the birth and death indices. So basically this collection will of co-cycles will keep changing, and the matrix H will change accordingly. So this is the co-cycles of ordinary persistence that we maintain. And using with the help of this matrix, we compute another matrix, and this matrix is S. And the way this matrix is maintained is basically you maintain a set of co-cycles which are product co-cycles. So these are co-cycles that are found using products of co-cycles of ordinary persistent of representatives of ordinary persistence, and these will for every K the classes of the co-cycles that we maintain in S will form the vector space VK. Remember that V bullet is the persistence module that we are dealing with. So VK is the kth index vector space. So we maintain these two matrices, and we have two cases to consider. So the first case is when the index k in the for loop is a birth index of the ordinary persistent cohomology, and we recall that one of the properties we show is that the birth indices of the persistent cup modules are a subset of the birth indices of ordinary persistence. So if this is the case, that the index k is a birth index of ordinary persistence, then it could potentially be a birth index also of the persistent cup module. So we check if it is so, and we do this by taking the product of all the co-cycles zeta j in H with the co-cycle zeta I, where zeta I is the representative of bi di, and your k is the birth index bi. So we take all these products, and using an independence check, we see if we can augment the basis that is maintained in the matrix S, which contains the set of product cycles that are alive at this point. So if we can augment this basis, then we do so, and we annotate the birth index of this co-cycle by k. So that means that we have found a new interval, and we now know only its birth index. The second case is that of death. So we recall that we also showed that the death indices of the cup modules are a subset of the death indices of the ordinary persistence. So we want to see if it is indeed so, and we only need to check so at most one cycle, a co-cycle can become 0 in this iteration, and we check we do a matrix reduction to check if there is indeed a co-cycle zeta that becomes linearly dependent on the other co-cycles that are maintained in S. And if this is so, then we have found the depth index of an interval in the cup module, and because the representative xi becomes 0, and we already know its birth from a previous iteration. Now we also know its death, so we have found an interval k comma zeta birth, and we generate this persistence pair. So that's a brief description or a high-level description of computing a persistent cup module. So the implementation details is that how do we maintain these matrices H, and S? So there are 3 points to note. One is that this matrix H is initialized with the essential co-cycles of ordinary persistence with degree greater than 0. The matrix S is initialized with the co-boundary matrix of the complex. And because the maps on cohomology are given by restrictions, we maintain the co-cycles in S and H by restricting them for every index k. Then the last thing to note is that for the when it's a case of a birth index, then we appropriately add co-cycles to a matrix H and S, and if your k is a death index of ordinary persistence, we appropriately add we appropriately remove the co-cycles that are no more living in matrices S and H. So that gives the final details of the algorithm, and now I'll give a brief analysis of why this algorithm takes O(n) raised to 4 time. So the first thing to note is that computing the barcode of ordinary persistence and computing persistent cohomology basis can be done in O(n) cube time using standard algorithms in persistence literature like a PICO or a compressed convolution matrix. Then restrictions of co-cycles and index k can be done in O of n time. And this is simply by deleting the row k. Then the independence check of co-cycles in the matrix S can be done in O(n) squared using standard matrix operations. And note that there are at most n choose 2 pairs to check in the course of the algorithm. So, and this check can happen somewhere in the for loop, but it happens at most once. So there are n square pairs to check, and each of them takes n square time. So the total time for this step is n raised to 4. Then finally, in the depth case, we do a matrix reduction where we do left to right column additions and keep the matrix S in the reduced form. And this is like a persistence like reduction. And this takes at most O(n) cube time. And the outer for loop that runs from n to 1 is O of n times. So the total time is O(n) raised to 4. So all steps combined, none of them take more than O(n) raised to 4. So the total complexity of the algorithm is O(n) raised to 4. So now I'd like to conclude the talk by with a few remarks. So the correctness of the algorithm follows from an inductive argument using the rank function. The algorithms for computing persistent L-cup modules and partition invariants are structurally similar to the algorithm that for persistent cup modules that I explained in the previous slides. So that's why I focused on only that one algorithm. And finally, I want to point out that these algorithms use persistence like matrix reduction and will likely lead to a fast implementation. And in fact, we believe that a fast implementation of this invariant would make a significant impact on TDA practice. And this is something that we would like to consider as part of future work. So with that, I'd like to conclude my talk, and I would be happy to take any questions.
Thank you. Thank you. Yeah.
Yeah, interesting work. So do you have a sense of if you have a matrix coming from a point cloud, like in 3 dimensions, will you find a lot of persistent cup products or not? I see the torus, that gives us 1, but if we
the question, well, I mean, it would depend on the data set, and I guess it is of course one can artificially construct these kind of data sets, but what would happen in practice is something that one would know only after implementing it and testing it. But I'm optimistic that for practical data sets you would find something that's fine.
Or let me phrase a different version of this question, that often when we think about TDA, we think about finding kind of global large-scale structure, but finding those long bars is sometimes difficult. But then there's much more smaller features that maybe tell us something about the local geometry of the space. Have you thought about whether or not cup products maybe tell us something about local structure if you're sampling from, say, a Riemannian manifold?
That's an interesting question. We haven't really thought about this, but I guess it should say something which ordinary persistence fails. So theoretically, I don't know how to show this, but I guess, yeah, I mean, my answer is again the same, that one would have to see what actually happens in practice and play around and find a data set where something interesting comes up, and this would just be found out by dirting your hands and implementing it and showing that we found something and we can explain something that was not explained before. Thanks.
Thank you.
There is one question in the chat.
Could you run it out?
So the question says, it may happen that a generator X born at a time T and X begins to be a cup product element later after T. So how to describe such a phenomenon by persistent cup module or diagram?
Yeah, it may happen that a generator X that is born at T and X begins to be a cup product element later after T. Well, this does. So this is some. Yeah. Thanks for the question. Yeah. Well, so this is this does not happen, right? Because this is something we show that the birth indices of the cup module are a subset of the birth indices of the ordinary persistence module. So we have narrowed down what the birth indices are. So once you have narrowed down the birth indices to be the only ones possible, which are the ones given by the ordinary persistence barcode, then you just find if any of the cup products at the birth index of an ordinary of the barcode of the ordinary persistence, if you just take all the products that are born at that instant and see if you can extend the basis maintained in the matrix S that was shown in the algorithm. So if you can extend the basis, then you have found a new generator. And if you cannot extend the basis, that means there is linear dependence, or it means that there is nothing interesting happening there.